Scissors and okay.
Excellent, thank you very much. It's always nice to get a nice introduction, and I have no idea, but I assume it was excellent, and I can understand the word maths jam, so I did hear what some of that was about. I also heard the word fun run, and I have signed up for the fun run, which now that I've told 750 people, I do have to turn up, don't I, tomorrow morning. Okay, so my name's Katie. You've just heard a little bit about me, but to give you a bit of context, what I usually say when I go and talk to audiences in schools is I say that I am a mathematician, and what that means is that I studied maths at school, as often the people in the audience are currently doing. I went to university and studied maths there, and at the end of uni, I decided I still hadn't had enough maths, so I carried on, did a little bit of research into maths, and now a large part of my job is to talk about maths in various different places. So I go and visit schools, I do things at science festivals, I go on the television and on the radio, and I talk about maths on YouTube, just in the street, basically anywhere that people will allow me to talk about maths. That is where you will see me doing that. So that explains a little bit of why I'm here today, and I'm very excited to come and share with you some of my favorite things. And this is a collection of things that I put together on the topic of mathematics and paper. So hopefully, any second now. This is a new clicker. That's my complaint here. Come on. All right, just going to press that button. Hopefully this will start working at some point. On the topic of mathematics and paper, and it turns out there's quite a lot of things that you can say about mathematics and paper, and I've had to pick and choose, because obviously there are a lot more activities and a lot more things that you can do with paper. So I've picked out some of my favorites, and these are kind of inspired by something which happened to me, which is that I had a box of A4 paper, you know, just a box of paper that you would buy to put in the printer, and on the side of the box it had this label, and I thought this was a great kind of advert for what was inside the box. You know, they're really trying to sell the paper. They're saying there are some, you know, sheets of paper in this box. They're maximum quality. They're high definition. They're vibrant colours, which is, I mean, it's white paper. It also has ultra whiteness. I'm not sure how those last two go together. And it also had this, which I thought was quite amusing. Down the bottom there, it has double-sided use. I mean, again, that is something that I would expect as the very minimum from some paper, is that you can turn it over and it has a back. But in fact, all of these things are not the most interesting thing about this paper. And if you're trying to sell your paper, if you've got a box of paper and you want to say to people, this is the best paper, you should definitely buy this, the thing on that screen that I think is the most important is in the very top left. It says A4. And this paper is a brilliant shape. That's what I'm trying to say. This particular shape of paper is actually really, really clever. And it's the A4 paper ratio. It's the one that you're probably very, very familiar with. You probably handle a piece of A4 paper every single day of your life, especially if you're a maths teacher. There's probably a lot more paper involved in the life of a teacher than there is in the life of any other person. But A4 paper is something you'll be extremely familiar with. And there'll be one thing about it that you might be aware that you can do. So if you have a piece of paper with a thing printed on it, this piece of paper here says, this is a thing on a page. You can, if you want to produce two of these, just shrink it down. You can just do that. And it means that you can fit two on the same page. And that is not something that happens to every piece of paper. That is not something that happens by accident. And it's not actually something you can do with any old bit of paper. It's actually a very special property of this A4, which is that if you have a piece of A4 paper and you fold it in half, the rectangles that you get are the same as the original rectangle you started with. There is exactly one rectangle that does this, and it's the one they use for A4 paper. You could have a wider rectangle or a taller rectangle, but this is exactly the right one. And in fact, I can prove to you that this is exactly the one rectangle that you get. And in fact, in doing so, I can show you exactly what the sides of the rectangle are. So I've done the working out, and I've printed it on this piece of paper here. Is that too small? Can you see that? Actually, you know what? I can open this up, because it's just the same. I can just scale it up. Is that big enough? Not quite big enough? I'll open that up for you. There you go. So you can see there, can you see at the back? Maybe not. I'll just open this up. So this will hopefully show you, excuse me, the working out here. So what I've got is a rectangle on which I've got sides X and Y. And what I would like is that if I take one of those and cut it in half, that the ratio of the two sides, x divided by y, is the same as the ratio of the kind of half rectangle, which is y divided by x over 2. And if that is true, I've got an equation here, I can do some maths, I can mess around with it, and all the way down to the bottom here, I will get x is the square root of 2 times y. And that is the magic ratio. The square root of 2 is the number that gives you this beautiful property. And it's a lovely number, it's an irrational number, it's the square root of 2, and it is a fantastic thing. And I thought I would share with you some of my joy at A4 paper. So in fact, 1 in 3 of you has been given a piece of A4 paper. If you have got one, it's pink. So if you have a piece of paper that's green, that's a different one. But pick up the pink one if you've got one. And if you want to get a little bit of light on the room so everyone can see what colour the paper is. Okay. I don't know how do you quiet down a room of teachers? I don't know. I don't know what the protocol is here. It's your own time you're wasting. I'll keep you behind afterwards. Okay, so if you have a piece of A4 paper, you don't have to believe me when I tell you this fact. You probably do believe me, but you don't have to. You can use your own kind of, you can do your own experiment here to test. So if you have got a pink piece of A4 paper, if you can find someone nearby that also has a pink piece of paper, just look at them now, lock eyes with someone nearby. One of you fold your piece of paper in half, and the other one don't fold your piece of paper in half. So you'll have one half size and one full size. Okay, and what you can do now is you can look at your half-size piece of paper towards the full-size piece of paper, if you can get your cooperative friend to hold up the full-size piece of paper in the right place, and you can convince yourself that that is the same. And once you've done that, you can then swap. If you both want to convince yourselves, you can then swap and be completely sure that it works. Okay. Okay, I'm going to give you another 5 seconds to do that until you're completely satisfied. Okay. Okay, so I'm hoping you have convinced yourselves and the people around you that that is definitely the same rectangle. And before we move on from this, because I wanted to show you another nice thing you can do with A4 paper. And in fact, if you've not seen this before, this is a really nice little thing. So I'm going to put a camera up here so you can see what I'm doing. So what I'd like you to do is to take your piece of paper and take a corner of it. If you folded it in half, open it out so that you've got a flat piece of paper. Take a corner of it and fold it across to the other side like that. So you make a fold that goes through the corner, and you make a nice diagonal fold like that. Okay, so having done that fold, I'm going to ask you a question, because I want to know if you can, either if you know this or if you can work it out using a little bit of mathematics. So if this short side of the paper is of length 1, what is the length of that diagonal that you have just created? There is various chatter in the room. I'm hoping that you're all saying that it is the square root of 2. Because we've got a little bit of trigonometry here. We've got 1 squared plus 1 squared, and then we take the square root. It is also the square root of 2. So that's interesting. That's a nice, interesting fact. So I want you to make one more fold, and the fold that I would like you to make is this one. So I want you to take the other top corner that's at that end of the triangle and fold that down so that the lines match up. Okay, if you've done this, you are now holding a shape. And it is a shape that you've seen before and that you have a name for. And if you can't recognize what shape it is, it might help if you turn it round. This is, in fact, a kite. I'm not sure if it's the same word in every language, but it is a kite shape, and it has a line of symmetry down the middle. So that's quite a nice little, if you challenge someone to identify this shape, it doesn't immediately jump out at you, but it is a kite shape. And if you would like a further puzzle, And I'm just going to tell you this, and then I'm going to move on and talk about something else. I realize the folly of setting a puzzle that you then don't give people time to think about, but think about it afterwards in the pub at Maths Jam or discuss it with other people then. This shape that you've now created, if the original piece of paper had side length 1, what is the perimeter of that shape? And it does sound like it's going to be some kind of horrible thing made up of fractions and surds, but I will leave that one with you, and I'm going to move on because this is not the only nice rectangle. There are other nice rectangles out there, and in fact, one rectangle that people quite often like to talk about, especially in mathematics, is this one. And I've made it this colour for a reason, because this is a golden rectangle. Now this is, unlike the rectangle for A4 paper, which if you fold it in half, you get the same rectangle, this has a different property. If you fold a square off one end of it, just like we did with folding in the corner of the triangle, it will give you the same rectangle there at the end. So that's a different thing, but it's equally nice. And the ratio for this one is not the square root of 2. It's this number. It's called phi, or the golden ratio. It's square root of 5 plus 1 over 2. It's the only number that does this. So 1 plus 1 over phi is equal to phi itself. There is only one, well, there's two solutions to this, but they're either phi and 1 over phi. It's the only number for which you can do this. So you have two values, a and b. A plus b over a is equal to a over b. That's equal to phi. It's also this. It's quite a nice fact. It's also this. It's an infinite continued fraction of ones going all the way down. It's also, and I don't know when you're going to find this useful, it's also this. ... And it's also this. But anyway, it's a beautiful ratio, and people like it. People talk about it all the time. People have various fanciful ideas about the places that it occurs. And in fact, people quite often use it in architecture. So there are lots of historical examples of buildings that some people claim are using the golden ratio, or they're kind of quite close to the golden ratio. So let's just assume that they've done all the same maths as us. And in fact, there is a clip that I want to show you from a video here, which this is something that absolutely makes my blood boil, and I'm hoping you're all going to be very angered by this as well. But this was a clip from a TV program about architecture and about how architecture affects people's lives. And because people really like the golden ratio, someone has built an apartment where all of the rectangles in it are golden rectangles. And he was interviewing the architect who designed this building. And I just want to play you this clip. And I'm going to play it, and then I'm going to replay the bit that I'm really concerned about. So hopefully this will come through okay on the sound. We've had a couple of slightly, you might have noticed, we've had a couple of slightly technical hitches with the sound. Here we go.
What is the golden section?
It's supposed to be a proportion that is absolutely universally pleasing to the human eye. When it's applied to a rectangle, the short side is 1, the long side is 1.618.
Well, that's just like a normal A4 piece of paper.
Exactly.
So an A4 piece of paper is the golden section.
It is.
Just going to play that again for you.
That's just like a normal A4 piece of paper.
Exactly.
So an A4 piece of paper is the golden section.
It is.
It is not. And I'm pretty sure I've just explained why it isn't. It is a very beautiful rectangle, but it is very much not the same as the A4 rectangle. And in fact, I think the problem here is that she's printed a picture of a golden rectangle on an A4 piece of paper. And this gentleman is obviously very confused by this, and he thinks that anything that is printed on a piece of A4 paper just is that thing. So if you showed him a picture of a bus printed on a piece of paper, he would say, so you're saying that's a bus? And you could say, it is, and he would just believe you. So anyway, the A4 piece of paper is beautiful, the golden ratio is beautiful as well, but the thing about A4 is that, I mean, we use it in the UK, I've seen a lot of A4 while I've been here, I assume you use it here. It's used in almost all countries, but there are some places where they don't use A4 paper, and in America they have two standard sizes that they use. Two? I mean, what's that about? But this is a piece of letter. That's the shape of US letter paper. And it just looks a bit wrong, doesn't it? It just looks slightly wrong. And they also have this other size, which, that makes me feel sick. This is called legal. I don't know how you would, I couldn't live with that. But anyway, they use different sizes of paper. And while this is a horrific travesty, It's also the reason for actually some nice maths. There is a nice piece of mathematics, again to do with paper, which has come out of the fact that America uses a slightly different paper size to the UK, so I'm going to forgive them on that basis. And this is a story which goes back quite a few years now, but it's this chap. You might be able to tell from the picture that this happened quite a few years ago, but this is a person called Arthur Stone, who was a mathematician, and he was a British mathematician who went to work at Princeton in the USA. And the story goes that Arthur Stone took all of his notes over there with him, and he had his binder, and when he wanted to make more notes and put them in his binder, the paper was all the wrong size. So he ended up cutting a strip of paper off of every single sheet of paper that he was going to use, and he ended up with lots and lots of remnants, bits of paper lying around on his desk. And being a mathematician, he got to playing with these bits of paper, and he discovered a thing that you can make out of a long strip of paper, which is actually a really cool thing. And I wanted to show you a couple of examples of this. So I've got, I'll do this on the camera. So I've got one here, and this is one that I've printed out. And you can see this is quite a simple example of it. It's got two fold lines, so I'm going to make a fold there and bring that round behind like that. And I've got a little tab there. I'm going to tuck the tab around the front, and then I'm going to make a fold here as well. And I'm also going to use, this is a little bit of pre-gummed sticky tape. I'm going to stick that down onto that tab. So hopefully you now can see I've got a square thing. But this thing has got a front and a back. It's got two sides. And in fact, I want to keep track of that because that's important. So I'm going to do something to help me keep track of that. I'm going to put a 1 on each of these sides here. This is side 1, and I'm going to put a 2 on this other side here. And you can see now that I've got an object with side 1 and side 2. And it's made up of 4 little squares, so I might be able to kind of fold it to kind of make a crease between those 2 squares. So there's side 1, and that's not side 2. That's a new side. There's side 1. I guess that's side 3. I'm just going to label that one 3. Okay, so that's side 3. So you've got side 1 and side 3, and if I just close that like that again, I can put a crease down there. So it's side 1 and side 3. And if I turn that over, we've got side 1 there, and there's side 2. And it turns out what I've made here is an object with more than 2 sides. It has, in fact, got 3 sides. And it's kind of an interesting object. It's called a flexagon. And this is the word that Arthur Stone came up with to describe this. So, in fact, I've got some pictures of this happening. So that's the whole thing. I've put the 2 folds in. I bring that piece round, tuck it underneath, and then put that flat and stick it down on top. And it's called a tri-tetraflexagon. So there's a little bit of a nice naming convention here. So the first part of the name tells you how many sides the piece of paper has got, and the second part of the name tells you what shape it is. So this is a tetraflexagon because it's made out of a 4-sided shape, a square, and it's a tri-tetraflexagon because it has 3 sides. And in fact, the printout for this is something that I'm very happy for you to have a play with. I have got a few spares which I'll bring along to Maths Jam after this, but you're very welcome to print your own ones of these because they're quite, everyone's just photographing it, I love it. You're quite welcome to print these. That's a sheet with 2 of them on it, and you can just print them out and cut them out. But that is kind of the simplest one. And in fact, if I wanted to encode the information that I have from this object, I could say that's sides 1 and 2, and there's sides 1 and 3, and I can move between those 2. And this is how simple it is. It's only got 2 possible states. But I can make something more complicated. And there is a way to make this object. And I'll put this on the camera so that you can all see exactly what it is that I've got here. This has got side 1 and side 2. Presumably just a square then, I don't know. Well, let's see. So if I fold it in half like this, it's now got side 2 on both sides. Oh, and there's side 3. But in fact, if I do this and go that way, there's side 6. And if I go this way, I can fold it that way and hopefully open. Oh, there's 5. And if I go that way from 5, and there's 2 again. And this has in fact got 6 different sides. So this is a hexatetraflexagon. And these are lovely, and it's actually really easy to make. This is tragic, but I'm going to destroy this now just so that you can see how it's made. But if I open this out, it is just a square like that, and you basically fold it by bringing in the sides. So if I start here, I guess. I want to make sure that the numbers are in the right place. I'm assuming they will be when I've done this, but yeah, there we go. So you just rotate round and fold the edges in each time. And for the last one, you need to make sure that that goes underneath instead of on top. But that is a hexatetraflexagon, and in fact, that has a slightly more complicated structure. So, we've seen this one. I came in on the wrong slide. It's fine. This is the structure of the hexatetra. So you start with 1 and 2, and from there you can either go across to these ones or you can go up and down, and you can move in all of those directions, and that will produce this thing. This is a nice way to look at sort of networks and graphs as well. You can think about what possible structures you can get if you're given this object. Where can you get to from which other places? And in fact, the flexagons that Arthur Stone were playing with were not this one. This is a simpler one, which was discovered afterwards. But the one that he discovered was made out of a long, thin strip, and he folded it into triangles, because this was his sort of standard way of fiddling with a bit of paper. And he discovered that if you wrap the triangles round, you can make like a tube of triangles that wraps around itself. And if you bend that, if you fold it across some of the folds, you can fold it round into a hexagon. And if you do that, you get a hexaflexagon. And I've made a gigantic comedy hexaflexagon for pedagogical reasons. So this has got 1 and 2. And if I flex this, the way you flex this is you do that. And now I've got side 3. Yeah, so I'll show you the flex again of the flexagon. So that's sides 2 and 3. And if I flex it again this way, there's side 4. And this has got, again, 6 actual faces. It's quite difficult to find side 6 unless you know where it is. It's in here somewhere. And in fact, this was one of the things that, that Arthur Stone and his friends started to play with. And I say and his friends. He was based at Princeton University. They formed a committee, as all sensible people do when they discover a cool thing. It was called the Committee of Flexigation, the Flexagon Committee, and it was just Arthur Stone and a couple of his friends. I've had 6. A couple of his friends. A chap called Bryant Tuckerman. And Bryant Tuckerman, actually, I mean, they're all in their own right famous mathematicians. Bryant Tuckerman discovered a way to always guarantee you find 6, which is what I was doing, which he called the Tuckerman traverse, which is you just keep flexing it in the same place until you can't, and then you turn it round one and keep flexing it there. And a couple of other people, some guy called Richard Feynman, a couple of other mathematicians who happened to be around, and they got together and they worked out the whole theory of flexagons and what possible flexagons there were and how you could make them and what kind of bits of paper you would need. And if you are interested, the graph for that one looks like this. And the Tuckerman traverse is around the outside of that shape. So it means that you do get to every set of shapes, every set of pairs eventually. And you can do a simpler version of this, because this has got something like 30 triangles in it altogether. If you want a simpler, you can make a trihexaflexagon, which has 3 faces. And if you want to make one of those, a friend of mine has put together a really nice little gadget which lets you produce this. You take that, you print it, you fold it in half and stick it down, and then you wrap that round into a hexagon, and it will give you a hexaflexagon where the one side is plain, the other side has the logo of the institution where he works, and then the third side is your face. So when you find it, you're like, whoa, because it takes a photograph of you and prints it onto the thing. So whatever you put in front of the camera will end up getting printed on that third face, and it will arrange the triangles in such a way that that will work. So that's a bit of fun as well. But these are all very fun to make and to play with. Now, at this point, I'm going to have a little interlude. I'm going to show you a puzzle, just to give you a couple of minutes to talk amongst yourselves and try and work the answer to this out. This is a puzzle which involves an imaginary piece of A4 paper, not a real one, and I don't want you to cheat. So if you have got a real piece of A4 paper, resist the urge to use it. Just use your imaginary one. So I've got my imaginary piece of A4 paper here. There it is. I hope you all have brought yours with you as well. And in fact, I'll put a picture of mine up so you can see it. There we go. And the question is, I'm going to put the question up and I'll go through it slowly to make sure you're happy. If you fold a piece of A4 paper in half 3 times, always folding the long edge in half, so whichever of the 2 edges is longer, you fold it so that that edge gets folded in half, then cut all 4 corners off, how many holes will you make in the paper? And I'll show you, I've got a little animation to make sure you're happy with this. So if that's your piece of A4, the first fold is like this. Now that other edge is longer, so the next fold is like this, and then the third fold is like that. And if I now cut all 4 corners off that thing, like that, if I unfolded this in your mind, how many holes would be in it? Go. Okay. I can see lots of people imagining a piece of paper, which is lovely. Okay, so I'm going to cut you off there. That's all you get, but I am going to now show you my unfolding imaginary piece of paper. So if you have got an answer, you can now have it confirmed or disproved. And if you haven't got an answer yet, hopefully this will help you. So that's the full thing folded up. If I unfold the first fold, I get this. If I unfold the second fold, I get this. And if I unfold the third fold, I will get this. Okay, so some of you are celebrating. If you did have 3, then you're correct. If you had more than 3, you may notice now that some of those are not holes. I mean, the best question I've ever been asked was I gave this to a room full of students, and someone put their hand up and said, "Is it a hole if it's not a hole?" I was like, I think you've answered your own question there. So some of those are not holes, but that is hopefully a nice little puzzle. And in fact, you can ask yourself all kinds of questions about, you know, how many, if I do 4 folds, how many holes, and if I do 5 folds, and so on. There's a nice little sequence of problems there. Okay, so I want you guys to do something else now, because you've been sitting there quietly. I've got some other things on the chairs for you. So you should find that some of you, next to the people who had A4 paper, should have a thin strip of paper and a pair of scissors. And if you can grab those now, my hope is that you can at least see someone nearby who is doing each of these things. And what I'd also like is, I'm hoping you've got one of these with you, given the context of where you are and what you've been doing today, if you can also find a pen or pencil. So if you've got one with you, you can use it, and if you can borrow one from someone nearby. Okay, so here is my long, thin strip of paper. Mine is yellow, and yours are pink, I believe. And what I'd like you to do is I'd like you to use this to make something. And I'm strongly hoping that quite a lot of you will have seen this before. I'm going to promise you that I'm going to try and at least show you something about this that you have not seen before. If you know where this is going and you're worried that you're just going to find the next couple of minutes very boring, don't worry. Just remain smug and just wait until you see something you haven't seen before. So if I were to join the ends of this paper together like this, just sort of normally, I would end up with a cylinder, and that is a very boring shape. It's all right, you know, there's not that much to it. So instead I'm going to do something more interesting. I'm going to take one side of this cylinder and turn it over and stick it together. So what I'd like you to do very carefully is, if you see this sticky, your sticky patch is a slightly different colour. If you can peel that off, and when you've done that little bit of paper that you've just peeled off, I want you to put that in your pocket, because you're going to use that for something very important later. And the conference organisers will thank me very much for saying that sentence. But please put that in your pocket right now. And you should now have a sticky bit there so you can put a twist and then stick that edge down. And you should end up with an object that looks a bit like this. I'll give you another 10 seconds just to finish doing that if you have not yet. Okay, so this is an object with which I hope you are familiar, but if not, this is called a Mobius band. It's named after a mathematician called August Mobius, which is an excellent name, and it's just a bit of paper with a twist in it. Or is it? It's got a lot of really interesting properties, and I wanted to share a few of them with you. So if you ever see a Mobius band, or if you ever see someone encountering a Mobius band for the first time, there are two things that I recommend you ask them to do. The first thing is to get a pen or a pencil and to draw a line down the middle of the Mobius band, and keep going until you get back to where you started. And it turns out that sentence is more controversial than you think it is. So I'll show you what happens on here. If you have got your own, you can have a go at doing this. If you haven't got your own, you can either see someone nearby or you can watch this on the screen. But if you draw a line down the middle of this shape, you'll find, this is some excellent line drawing from me here, I'm sure you'll agree, you'll find that when you get back to where you started, depending on what you mean by that, something interesting has happened, because I've now reached the point where I started drawing, and I'm on the back. So I can just carry on, I guess. I'll just keep going down this other side as well. So I keep going all the way down here. Don't get pen on the table. And carry on until I actually get back to where I started. And if I do that, which I hopefully shortly will, there we go. I've now drawn a line all the way along both sides of the bit of paper, which is interesting, because I have been assured by a box that this paper has two sides. In fact, it was a real selling point for them. They were very excited about that. And it doesn't anymore. It somehow does not have two sides, because I've taken my strip of paper and I've twisted it. I've taken the front and joined it onto the back, and I've taken the back and joined it onto the front. So this piece of paper now only has one side, and it is just that one side that's there, and the whole thing has only got one side, and that's weird. So this is weird. And if you show this to people and get them to really think about what's just happened, before they've done anything else, this is already kind of weird. And then the second thing, which almost everyone should at some point in their lives attempt to do with a Mobius band, and this is the reason why you have a pair of scissors. Short safety announcement before you do this. What I'm going to ask you to do is to cut along the line that you've just drawn, but, I mean, this is just general life advice. Don't stab yourself in the hand. I mean, just remember that every day, and you'll be okay. But I don't want you to try and just punch a hole through the paper with the scissors. What you can do is you can pinch the end together like that, make a single cut to start from, open it out, and then you can cut all the way along that line. So have a go at that now, if you're going to do that. I'm going to attempt to do it slower than everyone else. There's at least 3 or 4 people in the room are like, oh, sorry, I did that 20 minutes ago. Okay, if you have successfully done that, or if someone nearby has successfully done that, you might have heard them make a weird noise. That's normal. Because what happens here is something that is very much not normal, is that when you cut this object in half, you don't get two things. As with most normal, well-behaved objects, if you cut them in half, you would create two of something. This is just one thing. And it's a Mobius band, so this is why this happens. And the object that you get is not a Mobius band. And I can prove that to you. Because the reason why this happens is that the Mobius band, when you put your twist in it, not only has it only got one side, it's only got one edge. because it started off as a strip of paper with 2 edges. I put a twist, and I've joined one edge onto the other edge and the other edge back onto the first edge. So there's only one edge, and it wraps around the whole thing twice. And when you cut that in half, that one edge becomes the edge of this thing. So there's only one of them. So it's a big, long piece. But in fact, you can see here, this has got 2 edges. And you know that's true because one of them has a line drawn down it and the other one doesn't. You can see the line that I originally drew. And that means that this is not a Mobius band because it's got 2 edges. This is, in fact, a 2-twist Mobius band. This is the same as if I took a very long piece of paper, turned it over again, and then stuck it down. And that is a different thing. And the Mobius band has so many possible things that you can do with it. I'm going to quickly show you a few more. So I'm not putting out hundreds of strips of paper for you to all do this, but I wanted to show you a few of them, and I will try and stand still enough that the camera does not keep cutting out like that. Not sure what's happening there. Is it me? These things are all... That's a sound cable, it's not going to be that. That's worrying. Well, anyway, I'll just check whether it's this. Yeah, it looks like the laptop isn't feeding that anymore. I don't know if that's something. I'm just going to stand here and cut up bits of paper. If anyone wants to worry about that, please do. So this is another Mobius band. And what I'm going to do this time is instead of cutting it in half, I'm going to cut it into thirds. By which I mean I'm going to start 1/3 of the way across the Mobius band, and I'm just going to cut around in a straight line. I'm going to try and stay 1/3 of the way across. And if I do that, the first thing that will happen is that when I get back to where I started cutting, I'm going to be on the other side, which I now am. So I'll just keep going. This is usually my solution to any kind of weird thing that happens with a Mobius band is to just keep going, and eventually I will get back to where I started, and it will join up. But now I've cut the whole thing in half. Well, I've cut it in thirds. Of course, they're going to be 3 pieces, surely? No, there's 2 pieces that are joined together. And if you've not tried that before, that is lovely. The short piece and the long piece is what you get here. And the short piece is, in fact, what used to be the middle of your Mobius band. And the long piece is the outside edge, which you've just cut off. And there was only one of them. So obviously, there's just one of those. And it's looped through there because in order to wrap around the whole thing twice, it has to go through that hole in the middle. So that's exciting. I wanted to show you another thing that you can do. This is with, see, that's what you need. This is with 2 untwisted Mobius bands. So you can put, 1 twist, you can put 2 twists, you can put 3 twists if you're feeling really flush. If you've got a lot of twists on you, you can put 3 twists in a Mobius band. That's quite cool. But these are 2 Mobius bands with no twists, and I have stuck these together at right angles to each other. So if I put this here on the camera, you can hopefully see exactly what object I've got here. And what I'm going to do is I'm going to cut both of these in half. And I want you to have the 30 seconds while I do this to discuss with the person next to you, what will I get if I cut both of these in half? Go. Okay, stop discussing. If you've not worked it out by now, I'm going to show you what happens. You get square. Yeah. Yeah, exactly. A square. My favorite thing is if I've done that and someone's just walked in and I go, a square, and everyone goes, oh, wow, excellent, and then starts applauding. It's just a square, calm down. No, it's really good. It's so nice. And the best thing about this, when I first saw this, someone showed this to me, I could not guess what it was going to be. And I was trying to picture it and trying to manipulate this thing in my mind. I couldn't get it. They showed me. And then when I saw it go back together, it all just made sense. So that is the kind of halfway stage that you reach. And then if I bring those round, that is your 2 circles again. Does that help? that kind of helps, doesn't it? So that's the thing we originally started with 2 cylinders, and then I open it that way, and I open it that way. And the 4 corners of the square were all together in the middle, and the reason I've got 4 right angles is because I made 2 cuts that crossed each other at right angles and created those 4 corners. Now, I've shown you that, not just because it's lovely, but because that's kind of level 1. That is 2 Mobius spans stuck together. Yes, so we'll see what happens here. In fact, while I do this, rather than ask you to try and guess what's going to happen, I will explain how you do this, because this is not as simple as it looks. So in order to make this, you need 2 Mobius bands that twist in opposite directions. So when you make a Mobius band, you kind of have to choose whether to twist to the left or to the right. And if all you're going to do is cut it in half and go, ooh, then it doesn't matter which way you twist because they both behave in exactly the same way. But if you want to do this, you need 1 of each. And the real challenge there, sorry, that's the halfway stage. It's not really giving you any clues. If you want to do this, you need to make a Mobius band, and then the real challenge is remember which way you twisted it, and then make another Mobius band that twists the opposite direction. And my main advice is don't try and do this while people are asking you questions about technical setup, because that's what I did. I'm terrified this is not going to work, but we'll see what happens. Oh, no, it's worked. You get a pair of hearts linked together. Yeah, I'll hold that up there so you can see. Yeah. That's unbelievable. So this is one of the most romantic things in maths. I'm just going to go out on a limb and say that. And it's another one of those things that the Mobius band does that you think, what? What's just happened? But you can understand it a little bit. So, in fact, in our square, we had 4 right angle corners. This has also got 4 right angle corners, if you can spot them. There are 2 here, and there are 2 up here on the points of the heart. So there are still 4 right angles. They were what used to be in the middle when I made my 2 cuts. And you can see I've used 2 different colors of paper. So each of these was originally 1 Mobius band. So half of each piece of Mobius band has gone into each heart, which, if that's not a romantic metaphor, I don't know what is. And they're linked together because Mobius bands are stupid. So that's a nice little thing that happens. And you know, that's one of the reasons why I think Mobius bands are lovely enough to include in this talk. They're also useful. And I mean, people just think of these as a thing that you cut up a bit of paper. They're also used with very limited applications as drive belts, because it's only got one side. So instead of having a drive belt where you wear out the inside of it and then you have to throw it away and get a new one, it wears both sides evenly. Yeah. And this is a very, very old patent application. I don't know how much this is actually practically used by people, but it is a principle that you can make use of. There is also a Mobius roller coaster. And it looks like this, and it is brilliant. I've not been on it. It's one of my dreams in life to go, have a go on this roller coaster. But there are 2 trains on the same roller coaster, and they set off from the same station, and then they go off, and one of them immediately dips underneath. So it's like the 2 edges of the Mobius band. So there's a twist, and they go all the way around the roller coaster, and they come back the other way round. And everyone who was in this carriage was looking previously to the left at their friend in the other carriage, suddenly finds they're on the wrong side. Like, what? Because it's a Mobius. Amazing. Okay, so that's another nice thing about Mobius bands. So I think there is one more thing that I want to show you about paper, and I think I'm gonna move on to that now because I am aware that I'm going to finish on time. So this is a thing which I discovered. Actually, I discovered this while I was making my hexatetraflexagon. Yes, that's what it's called. So if you remember, this is a square with a square hole in the middle. So I had a piece of paper, and I wanted to cut out a square hole from the middle of a piece of paper in order to make one of these. And I thought, all right, get my scissors, safely cut. I'm not going to just jab a hole in it. I'm going to safely cut a little thing and then cut around. I thought, no. I'm a mathematician. There must be an easier way to do this. Because if there's one thing about mathematicians is they're very lazy, and they will always try and find a cleverer way to do something. So I had this piece of paper with a square, and I wanted to cut the square out. And I thought, you know what? I can fold this in half, Because this is what you're all thinking. You're thinking, fold it in half. And now you don't have to cut 4 sides on the square. You only now have to cut 3 sides. I was like, great, I've reduced the number of cuts that I need to make from 4 to 3. And then I thought, no, it's not good enough. It's not good enough. I want fewer than 3 cuts. So I thought, okay, I'm gonna fold it again. So I folded it in half the other way. And now I've got 2 cuts. Very satisfied with that. 2 cuts. That is surely the fewest. No. So I realized there was definitely going to be another step to this, and I'm sure you're all miles ahead of me here, but I realized that if I did another fold here, made a nice diagonal fold, now I only need to make 1 cut to cut out the whole square, and I'm going to do this now. It's not as impressive as I might have made it out to be, but if I do this with 1 straight cut, I can cut out this whole square. And I also have not damaged the outside bit, which was obviously my goal because I was trying to make a thing with a square hole in it. And this got me thinking, and I went down to the pub because it was Maths Jam, and some of my friends were in the pub, and they were all mathematicians, and I said, check me out, check out what I've just done with a bit of paper. There wasn't much else going on. I was like, look at this thing I did. And they said, one of my friends who happened to be sat there said, isn't there a theorem about that? And I was like, yes, I'm going to look this up. So I looked it up, and there is a really, really nice piece of maths based on this. And what I'd like is to talk you all through doing a thing at the same time. So there is one remaining type of bit of paper out there. It's a green bit of paper that you should have. And I'm hoping you can follow along with this. I'm going to expect roughly 30% of people will not manage this because it's not an easy thing to follow at all. I'm really hoping you can get this to work, but we'll see. So we're going to start off with the piece of paper. This is not a full A4 piece of paper. It has been trimmed to a very specific size, but I would like you to still hold it in the portrait orientation, so it's slightly taller than it is wide, if you can manage that. And I want you to, first of all, fold it in half across the middle like that. Okay, it should now be very resolutely wider than it is tall, so keep it that way around. And the next thing you need to do is make 2 creases. So crease it that way and crease it vertically as well, and then unfold those creases so you've got the same thing back again. Okay, so you've made those 2 folds. They should now be merely creases, but I want you to make sure that the side with the fold, the thing that you originally, when you folded it in half, is still at the top. That is very important. If it's at the bottom now, this is not going to work. So at the top should be your folded edge, and I'll zoom in on this so we can see what we're doing a bit better. So what you need to do is we need to take one corner of this and fold it across onto the paper, but there are a couple of very specific points. So you need to use this corner, and you need to use a fold which brings it across here. So my recommendation is that you put your finger at the top there. So your finger goes on that crease, it's giving you a point in the middle, and you want to hold that there so that when you bring this across, the top edge of the fold goes to that point. So you're going to end up with this. And if you can see that happening on there, so it's going to land on the horizontal line, and the crease is going to go up to the middle of the piece of paper. So that specifies exactly where your fold needs to go. There are some smart people who are leaning forward and using the floor as a table surface, but I'm hoping you've all managed to get something along these lines. Okay. So having done that, remembering this is top edge is the edge with the crease, so with the fold already, and you're going to bring it from that middle point down to there. The next thing to do is to take that corner, which is the corner you've just landed there, and bring, your finger's gone, and bring it back across, like make a fold down the middle of that section. So bring it back over to there. So you're kind of folding that edge onto the right-hand edge of the whole thing. Okay? There are 2 more folds. We're very close to the finish here. So the next thing you want to do is I'm doing this the opposite way around to that. But on the picture, the right-hand section, you want to bring that behind so that you're folding it along that line. So you're folding the back piece of paper, but along the edge of the other piece of paper. So it comes across the back like that. You can. I can go back one. Yep. So from there, you then want to fold that corner back across the other way so that you fold that front part in half. Okay, then you make a fold straight down that middle of the back section and flip it behind. And then you should find that the back section now that's sticking out is the same size and shape as the thing that you've already got, so you can do another fold round the back and lie it straight on top of everything that you've already got. So you end up with something that looks like an ice cream cone upside down. Okay, and you've got a right angle corner on one side where the corner of the folded paper is. Now, for this next step, and you might have anticipated this given what I was talking about earlier, is that you need to borrow a pair of scissors from someone nearby, which hopefully there is. And I want you to make one straight cut. One cut, no more than one, absolute maximum laziness possible, from the right angle, the corner there that is a right angle, just diagonally across. And I'm going to recommend an angle like that, but it doesn't really matter exactly what angle you go up at, just towards the middle of the other side. And if you've done that, you should be able to unfold the shape that you've just made and see what you've got. That was an excellent noise from a whole bunch of people who opened it out at the same time. But if you have done that correctly, and if you haven't, it's very much not your fault. You should end up with a star shape, something with 5-fold symmetry, and depending on what angle you chose, it will either be very pointy or very fat, or somewhere in between. Okay. Thank you. Thank you. So, I think the best thing about this is that you also get a hole the shape of a star, because you've only cut the edge of this shape. You've not kind of hacked away pieces to obtain the shape. You've literally just cut along the edge of that shape in one cut. And I want to show you one more thing to do with this. So the star, the folding pattern for the star that I've just shown you is actually something that's quite widely known, and there is actually a bit of a myth, a bit of a legend associated with this. And it actually originates in a country where stars are really a thing. They really like their stars, and that is in America. And in 1770-something, I guess, when they were originally deciding on what to put on the American flag, the story goes, this is entirely false, it's completely made up, but the story goes that George Washington went to visit a seamstress called Betsy Ross and said, "We like stars, can we have stars on our flag?" And Betsy Ross said, "Of course you can have stars on your flag, I can make whatever flag you want, I'm a seamstress." And George Washington said, "We kind of like 5-pointed stars, but we realize they're really difficult to cut out." And Betsy Ross said, "No," got a bit of fabric, folded it up and cut a star in one cut and showed him. And he was so impressed that he immediately said, "Okay, you can make all the flags." So for the rest of her life, she was just employed making flags. She had work for life, which I guess in those days was a rare thing. And it's probably not true, but I love the fact that she just used some maths to impress someone, which is essentially my job now. So she was like the precursor to me. And this is a lovely story. We don't know if it's true or not, because it's one of those sort of legends that's cropped up around it. But there was a person called Betsy Ross, and she did make flags in the early United States. So that is where that originates. And In fact, I wanted to finish by showing you one more thing. I know I'm slightly over time, and I'm really sorry, but we started a little bit late. Let's go with that. This is the best bit, essentially, so I don't want to miss this bit. Before I do this, I'm going to need a volunteer who has a name with 4 letters. So if your first name has 4 letters, if you can put your hand up so I can see. Who have we got? We've got a person here who's both volunteering and being volunteered. Oh, you're not volunteering, but other people are volunteering you. What's your name? Jill. Is that with a J? Jill? Okay, fantastic. So the thing I wanted to tell you about this is actually from, there is a theorem. There is a piece of maths to do with this. And because mathematicians are imaginative at naming things, it's called the fold and cut theorem. That's just what it's called. And it was a group of mathematicians basically have worked out the answer to the question, if you have a piece of paper and you can fold it as many times as you want, what shapes is it possible to cut out with one straight cut? And the answer to that question is any shape. So it turns out whatever shape you want, you can cut it using one straight cut, which is quite a nice little fact. And they've proved this. They've got a proof and a paper about it. And it's essentially they've worked out an algorithm. They've got a method which, if you give it a picture, will tell you then a set of fold lines to do to cut out that shape. And in the paper, they have a little preamble, a little introduction talking about this particular question and the history of it and, you know, what people have done before. And in fact, they tell the story of this 5-pointed star. And in fact, they know a fact about it that I didn't know, which is that Harry Houdini, the magician, used to do the star as a magic trick in his stage show, which is kind of cool. So I come from a long line of people who stand on stage and cut out a star using one cut and impress people. And in this paper, they also mention that, because it's just a lovely puzzle. You know, it's a really nice challenge to take a shape and say, how would I fold a piece of paper so that I could cut out that shape? And they also mention that they had heard of a person who could cut out any letter of the alphabet using one straight cut. And I saw this in the paper, and I thought, all right, I'll have a go at that. So I sat down, and I worked out a pattern to fold a piece of paper for every single letter of the alphabet so that one straight cut would produce that shape. So I've done some folding. You've just seen me do some folding, and I've got 4 folded up bits of paper. So I'm going to do these 4 straight cuts. You might be guessing I'm quite near the big finale here. So if this does work, you know, go wild. If this doesn't work, please be nice. I mean, you've got 2 of the same letter in your name. Thank you. That's very kind of you. And nothing too difficult, I'm going to say. There are more difficult letters than this. For reference, capital R is horrible. And my absolute crowning achievement is the ability to cut out S, which is equally horrible. If you want to see proof that I can do this for other letters, genuinely come to Maths Jam, because you can just sit in the bar and command me to cut up bits of paper all night. But I can also, I can show you photographic proof, which is this. That is the whole alphabet done using one cut for each one. And I'm now going to slowly unfold these and hold them up. I'll put them on the screen so you can see. So that is, I'm pretty sure that's a J. There. Hold that up. Yeah. Okay, you are allowed to not be impressed by this one. That's I. Yeah. And I'm going to put an L there. And this one is the same again. That is also an L. And thank you. And what I will say is, Jill, you're very welcome to come and grab these afterwards. You can have the star as well. If you want to play with this, do, because this is an absolutely lovely little puzzle, and you can set yourself challenges. You say, here are some simple shapes. Can we cut out these shapes? More complicated shapes. Letters of the alphabet are horrific, but I have found a PDF. After I worked them all out for myself, I found a PDF that someone had already made that has all of the fold patterns for the letters of the alphabet, but mine are better, I'm going to claim, and there's a whole bunch of other resources. So if you would like any more resources on this, you're very welcome to drop me an email. I'll put my email address there. I have some videos on YouTube. I've also got a couple of videos on the channel, number file, including one on the fold and cut theorem. And I very much enjoyed. You've been a lovely audience. I'm going to finish there, so thank you very much.